Okay, so hello again, Year 8. Right, basically, we have come to the end of our topic on waves and the electromagnetic spectrum. So this session, we're just going to be going over what we covered, just sort of a bit of a quick revision session, really. So let's have a look. Can anyone remember some of the features of a wave? In particular, we'll look at transverse waves first off. So, okay, waves are undulations or ripples, okay? In the case of water, they travel through the water with a transverse motion, hence the name transverse wave. And this means that the up and down motion, or the undulations, actually travels at, the up and down motions are at 90 degrees to the direction of travel. Okay, another example of a transverse wave is light. Okay, now light and color. Okay, if you remember last week, we went over Newton's experiment that proved that white light is actually made up of a spectrum of colors and it isn't pure as was the common belief. Okay, now within that spectrum of light, the light waves that create the different colors or represent the different colors are at different frequencies. Okay, that is the number of complete wave cycles within a second. So the higher the frequency, the more there are, the lower, obviously, the lower. Okay, so the higher frequencies of light are seen as blue and violet, whereas the lower frequencies tend to be red. Now, our eyes can only actually detect the three primary colours, your red, your green and your blue. Okay, and as I said before, this is due to a specialised cell in the back of our eyes called a cone cell. Okay, now these cone cells pick up the different waves of colour. Now, if one of these specialised cells isn't working properly, you will not be able to see that colour, hence we get colour blindness. Now, light can be reflected and absorbed differently by different objects. So lemon will appear yellow because it absorbs all of the colours apart from yellow and reflects that back into our eyes, so we see yellow. Now, this video, again, is just Brian Cox, and it's just going over what I said.
Is made up of all the colours of the rainbow. And when it reaches the earth, those individual colours are revealed.
Photons from the sun rain down and into water droplets. They reflect off the rear face, out of the front again and into your eye. But the blue photons, the higher energy ones, behave differently to the green ones and the yellow ones and the red ones. They come out at a shallower angle, and that's why you get the full spectrum of colours from the white light of the sun.
And it's this light that paints the earth.
Okay, so colour. What is colour? Okay, sorry about that. As I said, white light is a mixture of the many different colours which all have a different frequency, and the white light can be split into a spectrum through the use of the prism, one of these glass triangles basically. Okay, so the light comes in, it refracts, and they come out and you can see the different colours. Now there's 7 colours that make up the white light. I'm not going to go through them, you can see them there. Okay, as I say, the frequency is the lowest, which is the fewest waves per second, to the highest, which is the most waves per second. So if you remember, red is the lowest and the blue and the violet is the highest. Now, as I said, light's refracted or bent as it goes into the prism, and because of the different frequencies of each colour, they are refracted at slightly different angles, which is why the colour is split or separated, okay? And this is a process called dispersion. Now, light waves, okay? Speed of light is 300 million meters per second, okay? And that's in the air and it's in a vacuum, okay? A vacuum is space. There are no particles for the light to cause to vibrate and travel through, like sound, okay? Light travels about 1 million times faster than sound, okay? Which is why you see the flash of a firework before you hear the bang, or you see lightning before you see hear thunder, okay? Light moves in waves, okay? As I just said, it doesn't need a particle or particles to travel through like water or sound waves, okay? And that is why it can travel through the vacuum of space. Okay, light will always travel in a straight line. You can detect the light waves with your eyes and instruments such as cameras or lenses. Okay, they change direction when they pass through a point where two different mediums meet, such as going from air to water, or when it enters a glass block. Now, again, just a nice little video here, just because it is.
Light is a wave, like sound or water waves. But unlike sound or water waves, light waves don't need particles to travel through. Light from the sun travels all the way to the Earth through the vacuum of space. And light waves are 1 million times faster than sound. That's why when you see a firework go off, you see the flash before you hear the bang.
Okay. So, as I said, they are transverse waves, the light waves. They're faster than sound. They can be reflected, refracted, or dispersed. Okay, now, when we are looking into light waves, we tend to use something called a ray diagram. Okay, and the ray diagram shows us how light travels and what happens. So, we always use a straight line with an arrow depicting the direction of travel. You can see the ray of incident or the incident ray coming in here. We've got the angle of incidence, which is the angle away from normal, which is 90 degrees here. And we've got the reflected ray coming out here with the angle of reflection there. Now, if you remember from the previous lessons, the angle of incidence will always equal the angle of reflection. Okay, now, this is an example of a ray diagram on a smooth mirror. Okay, now if light hits a rough surface, each of the light rays obey this law of reflection, okay, where the angle of incidence equals the angle of reflection. However, because it is a rough or an uneven surface, each of these light rays is shot off in a slightly different direction. So if you imagine that this mirror had bumps all over it, one ray would come in here and go off here. One ray would come in here, it would hit a different angle of the surface and it would come off here. So it means that the light isn't actually reflected back in one direction. It's sort of spread out or scattered, okay? Now, this is an example of diffuse scattering, and it explains why you get a nice clear image and you can see yourself in a shiny mirror. However, you can't see it in a dull painted wall. Now, as I mentioned, refraction is where the light waves are bent, okay, and it is caused due to the change of speed when they cross the boundary between two substances. As I mentioned earlier, an example of this is air and glass. You can see it if you use one of the ray boxes at school, and you could carry this out at home if you get a torch, cut a slit through a thick piece of card, and basically shine it into a glass block if you've got one, and you will be able to demonstrate refraction. Okay, and it also explains why, if you ever have seen a pencil or a pen or something in the glass water, it appears to bend. It is because the image is distorted due to refraction and the light rays being bent. Okay, focus in. Okay, light can be focused, so it appears to me at a single point. Okay, this is how we get clear images and they're not blurred. This is how glasses work as well, because it focuses the light rays into our eyes. Okay, sound waves. Okay, what is a sound wave, or what is sound? Sound is vibrations. Okay, if you imagine a drum skin, you bang it, you get a noise. Okay, it vibrates. Okay, these vibrations of the drum skin cause particles in the air nearby to vibrate. Okay, they then cause surrounding particles to vibrate. Okay, and this is how the sound wave starts. It's almost like a ripple, again, how it moves across. Now, a sound wave is different to light waves. Okay, it is not a transverse wave, it is a longitudinal wave. Think about a slinky. Okay, again, sound can be reflected. Okay, it travels around about 343 meters per second through the air. Okay, and it actually increases speed as it moves through liquids and solids, because the particles that are vibrating are packed more closely together, so there isn't as much space in between them for them to lose energy and slow their vibrations. Okay, this is just a nice explanation, so enjoy.
Every sound that you hear will be different dependent on what type of room that you're in. So for example, if you're in this studio, it'll sound quite nice, hopefully. If you were to listen to the same sound in your bathroom, it might not sound as nice because it reflects off lots of hard surfaces. This studio has a lot of different surfaces, and they're all basically treated for sound. There's no windows in here. There's very little things that the sound can reflect from, unless we want it to reflect from those surfaces. On the ceiling, we have a sound diffuser, and what it does is it allows us to tell the sound where to go. So when a sound wave hits those directions or those pieces of foam, it sends them, to the left, to the right, back, forward, and it doesn't send them directly down where you're sitting. So it means that you get a much better sound.
Okay, so reflecting the sound waves on that diffuser to get them to surround you. Okay, so as I said, a sound wave is a longitudinal wave. Okay, and echoes are reflections of sound. Now, sound waves are longitudinal, and the vibrations travel in the same direction as the direction of travel. So, as I said, think about your slinky spring. You stretch it out, you jerk your hand forwards, and you get the compression moving along the slinky. Okay, now, as I said, when an object or substance vibrates, it produces sound. Okay, and these waves travel through a solid, liquid, or gas. They cannot travel through an empty space or a vacuum because there are no particles to vibrate. Now, the electromagnetic spectrum, okay, we covered this last week. Okay, it's remember my instructions, visible under X-ray glasses. Okay, so your radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Okay, as you can see, the frequency of the waves increases and they get smaller as they move towards, well, as they move from radio waves to gamma waves. Okay, they transfer energy as radiation from the source of the wave to an absorber. They can travel through a vacuum such as space, okay, and it will always travel, well, it will travel at the same speed through air as it will through a vacuum, okay? If you remember, the radio waves are huge, they're the size of a building, the undulations. Now, to calculate the speed of a wave, we use a triangle. Okay, we've got a distance, we've got a speed, we've got a time. If we know two of these, we can work out the other. It's fine. So if we need to calculate distance, it is simply just speed multiplied by time. If we need to find time, it is just cover it up and you say it's distance over speed, and that will give us how long it would take. And if we need to find the speed of a wave, it's distance divided by time. So if a child shouts to his friend, he's 50 meters away, his friend hears to shout 2 seconds later, how quickly was it traveling? Really, really simple. We want to find the speed. We know the distance, we know the time, so it's just distance divided by time. 50 divided by 2 is 25. So the sound was traveling at approximately 20, well, it was traveling at 25 meters per second. Okay, now, a bit of a whistle-stop tour on the revision there, but you have this video. There's loads of information on the slide, so please feel free to go back through, maybe pause and read through it. If you've got any questions, drop me an email. Use the previous lessons as well, because they will help you to really develop an understanding. Okay, have fun year 8 and speak soon.